Excuse me.
Okay, so what did I say? Again, so what we had earlier, what we have learned so far is that the pi electrons in the pi bond will be used to form a bond with hydrogen from the hydrogen halide to form your carbon hydrogen. And we are left with the carbocation for the other carbon. And once you form your carbocation, the nucleophile from the liberated halide here with its electron will be used to form a bond with carbocation to form your carbon next bond. Okay. And the usual hydrogen halides that we use in the electrophilic addition to alkenes, you have your HI, HBr, HCl, and HF. And you have the alkyl halide to be informed. So usually these reactions are carried out with our hydrogen halides, the one that I've mentioned in the solvent by dissolving them in the acetic acid or dichloromethane, or if we bubble this, the gaseous hydrogen halide directly to the alkene. So it's either we dissolve this in the solvents or we bubble this one in gaseous hydrogen halide directly sa atong alkene, whatever alkene that we have. And then for HF, usually for HF, it's prepared as polyhydrogen fluorine and pyridine. And the reactivity of these different hydrogen halides in the addition reaction, you have your HI being more reactive than your HBr than your HF. For reasons that this one, HI is much more polarizable and the distance between H and iodine is much larger than you have here. So the electron pair here can easily abstract the proton here to form your carbon hydrogen bond. Okay, as compared here. Okay, so HI is much more polar. For this one, the fluorine is very electronegative. It's very attractive to hydrogen. So the proton is much less available for the electron pair here to abstract the proton. So the addition of hydrogen halide, HX, to an unsymmetrical alkene could conceivably occur in two ways. There's actually two ways that, or two products that can be possible if we added one, but one of the product will be more predominant than the other. So for example, you have your alkene here, you have hydrogen here, and they have your alkene here, and your HBr can add for hydrogen here and Br here, like this one, and we eliminate the double bond. Or we can have our hydrogen here, and you have your Br here. Okay, the electrons from the pi bond. Okay, we can use that to form a bond with hydrogen. So if we form a bond with hydrogen using this carbon here, from the pi electrons here, you can form a carbon-hydrogen bond. And mawala si double bond, and then himo siyang positive, and then bromine will add to this, you get this one. The other one is if the carbon here will utilizes the pi electrons to form a bond with hydrogen. Okay, you have here another A. And what happens is that this one will become will become positive. So it will seek the bromine that you have in here, and you get this one. So there's two possible products. Okay, but the main product actually is this 2-bromopropane. And we'll explain later why would that be the case. And it is what we call, we follow what we call as the Markovnikov's rule. We'll explain that later. So if we have, for example, this one, 2-methylpropene, and we have HBr, again, your H can add either to this double bond carbon here, any of the carbon from the double bond. Okay, if your carbon here will utilize its electrons from the pi bond, so you can form a bond to hydrogen, and you have your bromine added diri si kaduha. This carbon will utilizes the electrons for this hydrogen here. You form carbon hydrogen, and then this one will have your bromine. Okay, so when this forms a bond kang hydrogen, the electron pairs diri kang bromine o kang hydrogen maadto kang bromine. Okay, and you will get a positive carbon here, a carbocation. So once you get your positive carbocation, the Br minus, the bromide, will utilize its electron to attack again this one, and then so you get your Br here. Okay, if the other carbon utilizes its electron pair from the pi electron to form a bond here, you get this one, and then the carbocation or the bromide is being released, will utilize its electron to form a bond here, you get this one. So again, for this two, the main product is this one, just a little this. Okay, so highlight the main product. So this, you notice this, that there is a trend for how this product is being preferred. This trend is what we call as the Markovnikov's rule. So this is discovered by a Russian chemist, Markovnikov. It states that the Markovnikov rule says that the addition of HX on alkane forms in such a way that the hydrogen atom adds to the carbon of the double bond that already has a greater number of hydrogen atoms. So let's say here, for example, this one, you see that there's a double bond carbon here, and CH2 and CH here. Okay, and one of the carbon contains a higher number of hydrogen. There is 2, and this other carbon here, there is 1. So it says here that for carbon that has already a higher number of hydrogen atoms, the hydrogen atom will, from the hydrogen bromide, from the hydrogen halide, from HX, will be added to here. Okay, so the hydrogen atom adds to the carbon of the double bond that already has a greater number of hydrogen atoms you have here. So this one will be added to the carbon containing higher number of hydrogen, and this will be left here with the positive carbocation, and that's where the bromine will be added. You have here. And so when we follow this rule, it says this is what we call as the Markovnikov's rule. And a simple way of remembering the Markovnikov's rule is that the rich gets richer, the poor gets poorer. So here the carbon here is much richer because it has a greater number of hydrogen than the other. So the hydrogen from the hydrogen halide will be added to this carbon containing already a higher number of hydrogen. So that's the reason you have in here. That's the reason that we say the rich gets richer, the poor gets poorer. And we can evaluate this one. No? So this one, you have 2 carbons here in the double bond. One has 2 hydrogens, the other has 1. And the greater, you will see according to the Markovnikov's rule, the carbon that has a greater number of hydrogen will have the hydrogen added to it. So here you have 2 hydrogens, so add hydrogen here, so you get your CH3. And then this is this carbon here, second carbon, will get the bromine. So CH3, CHB. And this one here, you have 2 carbons. First one, this carbon here contains 2 hydrogens, the other contains only 1. So this is the carbon that gets the hydrogen to get your CH3, and then this one gets the Br. Okay, and this is the major product. So although the other one, it's possible, but there's just very few that will be obtained for the other interchange CHBr to be added to double bond carbon. Again, so this one, the rich gets richer, the poor gets poorer, is what we call as the Markovnikov's rule, and you have your preferred Markovnikov product. So we can know more about this if you look at the mechanism. So next, the mechanism of the reaction following the Markovnikov's rule. Okay, so the first step is that the electrons will add to the proton. The pi electrons now will be used to form a bond with the proton, the hydrogen, and okay, if this carbon is the one that utilizes the pi electrons to form a bond with hydrogen, this first carbon here will be positively charged. Okay, it becomes a carbocation. And once the carbon is formed, balik-balik ako, no? Once the carbon is formed, the electrons from the bond here will be utilized, will go to your halide. So from 246, we mentioned 2468, and it will be free now and become negatively charged. So once you have your carbocation, okay, we use this kaning ito na form nga initial intermediate. Okay, and then you will have your halide attacking the carbocation. You get this one. So in the first step, you have here and the transition state, no? This is our first intermediate product here. To form this, you get a transition state. So this is our reactant, this is our product, this is our transition state. So you see here that the transition state, delta G here is much larger than the delta G2 here in the second step. So here you have the greater delta G, and we will consider this step 1 to be of a slower step, no, because the delta G is much higher, and to do that one, we have to climb the reactants. We'll have to climb very, very high energy. The reactants will really have to overcome very high energy before it forms this intermediate product here, as compared to B. Once you already once this two reacts, no, it's just overcomes a very small barrier of energy, a transition state between this and that before the product. Okay, to get this transition state, there is only a very small energy that's needed to overcome in order to produce the product. So between the two, the first step, actually the formation of the carbocation, is the one that is a slow rate determining step. And okay, the most important step is the rate determining step, which is the first one. And this step is highly energenic and has a high free energy of activation. You see this one? From here to this transition state, and this is our initial intermediate, the first product, intermediate product, okay, the carbocation. So from here, initial reactant, to here, no, it really has to climb very high amount of energy to form your transition state. What is the transition state to form your carbocation here? Of course, when the pi electrons will have to be partially broken. Okay, you have here partially broken, that, and there is a partial bond formation kang hydrogen and partial bond breaking process kang X. This is our transition state. Okay, and because of that, there is a partial positive charge being developed. Maklaro ba ang maklaro ninyo? Okay, you see here there is a partial positive charge on your developed carbon here. Okay, and this is the transition state. Once the bond is being formed, then there is a bond breaking process of double bond. Mawala ng double bond here and mawala na siyang bond. Okay, you have here, and then you have a positive charge. Okay, so once you get your product here, they will react. These two products, initial intermediate, will react again to form the final product. And what you will see is a partial bond formation here in the transition state, the partial bond formation from the carbocation and this halide we have here. And to do that, to reach the transition state, you only just need, or the system simply just need simply need to overcome a very small fraction of energy, small energy, to reach the product. Okay, and because of that, step 1 is the rate determining step. It is very important, to determine for the overall rate of the reaction, which is the case of forming the carbocation. And since that is the rate determining step, it is very important that we have to look the carbocation that's being formed, since step 1 is the rate determining step. And step 2 is the highly reactive carbocation combines the halide, and this step is exergonic. You have the product minus reactant, This is very low than that, so it's negative, it's exergenic, and it's a very low free energy of activation. So here you will see more of a more spontaneous process here. And here you will see this is an energetic process. So you have product, delta G is positive, is higher than the delta G of the product here. So this is an energetic process. This one, delta G, the delta G here is a product, it's much lower. And the delta G sa initial reactance is step 2. Step 2 niya kani, step 2. So you get a positive delta G. So this one is, positive. We get a negative delta G. So this one is more spontaneous actually. You get a negative delta G for step 2. This one is a positive first one. So this first one, step 1 is a rate determining step. So since it's the carbocation, formation of the carbocation is the rate determining step. Now we have to see what could stabilize our carbocation. So when we add when our alkene or the double bond will add to the proton from the hydrogen halide to form a carbocation. So we always have to prefer a carbocation that is much more stable. So if this one, the first carbon will add to the hydrogen, the rich carbocation containing higher number of hydrogen will add to this. This one di ay kanisang sa 2. What we get actually is if this first H2 will add to the hydrogen, no, what you get is H2 hydrogen bond formation here. We get a carbocation in this case. It's a 2-degree carbocation. No, so if the carbocation containing a higher number of hydrogen adds to the hydrogen of the hydrogen halide, you get a 2-degree carbocation in this case. But if the carbocation here, if the carbon here, second carbon is the one that uses the pi electron to form a bond here, you get a primary carbocation. So which one is more stable? Of course, we prefer a 2-degree carbocation, or if there is a 3-degree carbocation, it's possible, then we prefer that one. But in this case, you don't see any, but the most stable carbocation that we can obtain in the addition of our double bond of our pi electrons to the hydrogen, no, is the 2-degree carbocation. So this one is the more stable one, and this is the preferred pathway in the first step, no, the formation of this more stable carbocation. And this is the basis of the Markovnikov's rule, because here the carbon containing the higher number of hydrogen adds to the hydrogen adds to the carbon containing higher number of hydrogen, forming a more stable carbocation. And this is the basis of why the rich gets richer, the poor gets poorer, because there is actually a more stable carbocation that's being formed in there. So these two carbocations again, 1-degree or 2-degree carbocation, we already learned that in chapter 7. Now there is chapter 7 and chapter 6, they are not of equal stability. A 3-degree carbocation is much more stable than 2-degree and 1-degree. Again, unsa ganito yung reason nga more stable ang 3-degree carbocation? Anyone? What is the reason? Aiza? Anyone? Are you still there? Hello? Why do you think that a 3-degree carbocation is much more stable than a 2-degree carbocation? Hoy, ano man? Anyone? Madunggan ba ko? Na makadungog sa ako?
Dili kayo bulky, ma'am.
Dili kayo bulky? We need to find ways to stabilize our carbocation. Okay, there is a positive charge, no? So we need to stabilize that kung naatay intermediate na carbocation. And what is the way to stabilize our carbocation? Kanang positive charge. Unsa man, what are the ways? Anyone? Anyone? So we have to remember you have here a positive center. Okay, we need to find this carbocation is only an intermediate. No, it's not a final product yet. Okay, so we need to find ways. The more stable the carbocation, the more conceivable would be the reaction be. No, the more favorable that pathway be when the reaction follows the path of a more stable carbocation. So we need to find ways. We need to find a mechanism for which the carbocation can be stabilized. And one is that the more alkyl groups, okay, you have an alkyl here, R, CH3, and you have an alkyl here, CH3, no? Here, you only have one alkyl, CH3, CH2, even if dako na siyang alkyl, but still one alkyl attached to your carbocation. And this alkyl, okay, has an electron donating inductive effect. It can induce the positive charge. I-induce niya ang positive charge para somehow disperse ang positive charge which with each inductive effect. Kana bang i-donate niya by induction lang. Silingan niya ang electron density here. The second way and the most probable way of stabilizing our carbocation is the hyperconjugation. Okay, in the hyperconjugation, you have an sp3s here attached to your hydrogen. Okay, you also have here. They will stabilize that one by somehow an overlap, no, with a vacant p orbital here sa imong carbocation. I think I have already discussed that last time. Do not forget, no? Okay, so you have here this one. You have a carbocation here, and this is your alkyl group. No, you have an alkyl group here. Here is a methyl carbocation. You have hydrogen here. Here you have a 1 degree carbocation. Okay, and what you have here is a carbon that is bonded to 3 hydrogen. This is a methyl group. This is one alkyl group. So let's say your carbon silingan aning carbocation. So this carbon having a carbocation na siya unhybridized p orbital. Vacant na siya, wala na siya electron. Munang positive charge si carbon, no? Kay kulangan siya og electrons. And kulangan siya og electrons, gani si p orbital here, wala na siya electrons. Okay? And it is perpendicular to the plane of this trigonal planar sa imong carbon. So na siya silingan nga carbon, like an alkyl, any alkyl. Pag na siya silingan nga carbon, containing an sp3 orbital. Okay, so this, you have here a carbon hydrogen bond. Okay, sp3 s bond, sigma bond. So naano siya, and you can see this one is an sp3. It's a hybrid orbital. Remember, the sp3 is a hybrid orbital. It's like one sp3, 1/3 is an S character and 3/4 is a P character. Okay, sp3. So you notice here in the structure of the sp3 kaning yellow, no, mura siya may pagka P, and dako siya nga fraction is like murag P nga loob, gamay siya nga S. So if you look at this one, mura siya close siya nga perpendicular ani, pero dili gid siya perpendicular. No, remember that this carbon here utilizes a tetrahedral structure, di ba? So dili siya perpendicular like this one, but close siya to being perpendicular. And with that, it can actually share, no, by overlapping here sa iyang vacant nga electron here by what we call that one as a hyperconjugation. Okay. So what happens is that i-share niya with almost a parallel with the vacant p orbital by what you call as a hyperconjugation, by sharing sideways, no? And that is another reason why once you have an alkyl group, the hyperconjugation alkyl group adjacent to your carbocation, your carbocation, or your, yes, carbon containing a positive charge, no? Now, adjacent na alkyl group, it can actually stabilize that one by virtue of the hyperconjugation effect. Okay. Another way is if you have an alkyl, this one, aside from the hyperconjugation, you also have an electron donating inductive effect. And the third one is if naakay double bond, silingan the double bond, it can also stabilize the positive charge of carbocation. So there are three ways actually that can stabilize our carbocation. So do not always forget why a 3 degree is much more stable by 2 degree or 1 degree or that of a methyl carbocation. Okay, because of the hyperconjugation, because of the electron donating inductive effect, and because of the, if there is a double bond, because of electron delocalization. So there are three ways that can stabilize. In this case, wala tayo double bond, you only have an alkyl here. So here, the more alkyl groups, the more hyperconjugation will occur. So you have 3 carbon hydrogen here. There are 3 kani silang tulo can carbon hydrogen can do hyperconjugation ani kaning tulo ka carbon hydrogen can do hyperconjugation. So here it will exhibit more hyperconjugation as compared to Ria. Kini you only have carbon hydrogen. They will do duha lang ang possible nga magka-hyperconjugate to stabilize this one. So this second 2 degree carbocation can actually, or actually much more stable than the 1 degree carbocation. So remember the reasons, factors that could stabilize the carbocation. What are those? One is you have your hyperconjugation. What else? You have your electron of adjacent. CH. And then you have your electron donating inductive effect of alkyl groups. And if you have adjacent double bond or pi electron delocalization. Okay, so that is the reason again why you have a 3 degree, 2 degree, 1 degree. In this case, wala tayo silingan nga double bond. So Tama na taning duha. Okay. So these two carbocations, okay, so we always have to find ways, or we always have to choose rather the pathway that would lead us to a 2-degree, a much more stable carbocation. So the first one is when we add the proton to the double bond here. Okay, the first one, if the second carbon adds to the hydrogen, you form a 1-degree carbocation here. So if this carbon adds to hydrogen, you get a 1-degree carbocation. If the first carbon adds to the hydrogen, you have your CH3 and you get secondary carbocation here. And of course, between a 1 degree and a 2 degree, 2 degree is much more stable. So therefore, the pathway of this, the bromide adding to the carbocation here, there's only little of this products being formed. But if we proceed with using the 2-degree carbocation, we actually obtain the major product here. Okay, and this one is second step. This is the second step, which is very fast. The formation of the carbocation, the one is the one as we have already discussed in the mechanism. This first step is much slower in the formation of the carbocation. Okay, so the more stable the carbocation predominates because it is formed faster, and of course, formed faster man siya because it is much more stable. So this is the free energy diagrams for the addition of the HBr, HBr to propene here. And there's two pathways. No, the first one is the formation of a 1-degree carbocation, the broken line. The second one is the formation of 2-degree carbocation you have in here. And you notice that if we follow the second pathway where we form a 2-degree carbocation, the free energy, the delta G that we form in the first transition state to form our carbocation is much lower as we compare to the formation of 1-degree carbocation. Okay, and then you get your product here. So this transition state resembles this one, resembles a 1-degree carbocation. So here you will have your 2-degree, you have your alkene. Okay, so which atom here to form a 1-degree carbocation will be which carbon? Will form a bond with hydrogen to form your carbocation. So you notice here that you have the transition state, and our transition state ninyo, there is a partial bond formation kang blue, kang hydrogen. Okay, you have a dot. You have to know how to write the transition state, ha? And then there is a partial bond breaking process ng hydrogen and bromine. And then because they are forming a bond here, okay, there is a partial bond breaking process, a double bond you have here. So this transition state is much closer to this one. So once the carbon-hydrogen bond is fully formed, then the Br, the electrons from this will go to bromine, okay? And here, since it utilizes electron to form here one, get a positive. So this one, this transition state is much closer to this intermediate product here. And you will see for this kaning 2-degree intermediate, what you see is that to form this, your transition state will be formed kani. Now the carbon will form a partial hydrogen bond for me. You will have a partial carbon-hydrogen bond and a partial bond breaking hydrogen bromine and a partial bond breaking carbon-carbon here. And there is a partial developing positive charge here. And so this one is closest resemble this one. This is the Hammond postulate, remember. Okay, so again, so what you can see in here, the bottom line is that in the formation of a 2-degree carbocation, the pink one, the straight, the unbroken line, you see here, the delta G is much lower. And therefore, because of that, this is the preferred pathway to the formation of a more stable product. The reaction leading to the secondary carbocation has our free energy of activation, and this is reasonable because its transition state resembles the more stable carbocation and so on. Okay. So what else? So we will see the reaction of, we'll have another example for the reaction of 2-methylpropene with HBr. You can see here in the next slide. And here we will follow the same step. We'll first form our carbocation, and once you form our carbocation, then we have our product already. Okay, Sometimes there are cases now where we can do rearrangement, just like what we had experienced in 7.11, for as long as we will be able to form a more stable carbocation. For example, whenever natay-silingin a tertiary carbon, just like what you had in 7.11, in chapter 7 that we discussed. Now, for example, you get a 2-degree carbocation, but there is a possibility that we can obtain a 3-degree carbocation by rearrangement. Or for example, you have a 1-degree carbocation, but there is a possibility that we can get a 2-degree carbocation for due to rearrangement. Then sometimes that pathway will also be preferred to form our product. Okay, again, our goal is to find a pathway that would lead us to a more stable carbocation. So here, let's see, we have a reaction of 2-methylpropene, 1, 2, 3, 2-methylpropene, ano yung bromo? I delete, 2-methylpropene, okay, and to have our product here. So our other reactant is HBr. So how do we do that one? How do we do the mechanism? Okay, so of course, the first step is the formation of the carbocation. So either, again, you have to choose which of the 2 carbons will form a bond with hydrogen. So you will have to think if this carbon will form a bond with hydrogen, and it will utilize the double bond here to form a bond kang hydrogen. So you'll get carbon-hydrogen, and once the carbon-hydrogen bond is formed, okay, so of course the hydrogen isa lang dapat ka bond, so the bond kang hydrogen bromide will go to bromine. Okay, so if this carbon will form a hydrogen bond, carbon-hydrogen, you get a primary carbocation. But if this is the one, the first carbon will form a bond with hydrogen, you get 2-degree carbocation, and the bromine is liberated. You get this one? Okay, and what happens is that once you have your carbocation, then your liberated bromide will attack that one to form this. Okay, so it's not possible, katong akong gigan kanina, that this